Good morning, students. In today's lecture, we'll be discussing about the second part of digital transmission, that is analog to digital conversion. If you remember, in the previous lectures, we discussed about digital to digital conversion using different techniques like uh, line coding schemes, block coding, and scrambling. So, in today's lecture, we'll be discussing about analog to digital conversion, that is converting an analog signal to digital data. Reason being that digital data is being superior to analog signal. It is said to be more robust, it can easily be recovered and has ability to be amplified. So that is the reason in today's tendency that there is a change to uh, analog signal to digital data. Now this can be achieved using two techniques, that is pulse code modulation and delta modulation. Now pulse code modulation is also known as digitization, because we are changing the analog signal to digital data. So basically in pulse code modulation, when a signal, analog signal, is sent to a PCM encoder, it goes through three stages, that is three steps, you can say, like steps like sampling, encoding, and quantizing. Sampling is the first step in PCM encoder, wherein the analog signal is sampled in a duration say TS, that is sampling every interval. The inverse of sampling interval is called the sampling rate or sampling frequency, which is denoted as Fs, where Fs is the reciprocal of the sample interval. The three sampling methods are ideal sampling, natural sampling, and flat top sampling. Flat top sampling is also sometimes known as sample and hold. Now, in the ideal sampling, the pulses from the analog signals are sampled, but the ideal sampling cannot be easily implemented. On the other hand, we have natural sampling, wherein it is in natural sampling, it is a high speed switch is turned on for only this small period of time. But when we compare the third sampling method, that is the flat top method, it is the most commonly used sampling method, which, like I earlier said, is also known as sample and hold method. In this method, it creates a flat top at the samples. If you see the graph given in the figure 4.22, you can easily spot the difference in the third figure, that flat top sampling, the pulses are sent and it becomes stop in at some time, that creates a flat duration. Now these sampling processes are also known as pulse amplitude modulation, or in short PAM. Now according, if you remember the Nyquist theorem that we have discussed in the previous sections of this module, uh, just to recall, according to the Nyquist theorem, uh, the sampling rate must be at least 2 times the highest frequency contained in the signal. And if you just see the example that we have mentioned here to discuss this Nyquist theorem. Uh, just before that, if you see this Nyquist sampling rate, they have given for a low pass and a band pass signals. So when you compare these two graphs, you can see the Nyquist rate is twice the maximum frequency. that is the usual Nyquist rate. It should be the twice, at least twice the highest frequency rate. Whereas in the band part, in the band pass signal also, you can see the Nyquist rate is at least the twice of the highest frequency or maximum frequency. So just to elaborate this, there's an example to intuitive example of on an Nyquist theorem, wherein they have taken the sample of a simple sine wave, taking three sampling rates, that is fs sampling frequency, four times the frequency, which is actually two times the Nyquist rate, and sample one another sampling rate is twice the frequency, that is actually the Nyquist rate, and one is the frequency, just the frequency, the actual frequency. So the sampling frequency, they have taken the actual frequency, which is actually the one half of the Nyquist rate. So if you just compare the figure 4.24, the recovery of a sample sine wave for different sampling rates. So in the first figure you can see it is the Nyquist rate, wherein the sampling frequency is twice the frequency. In the sampling rate, wherein they have taken the sampling frequency as four times the frequency, it is becoming oversampling. In the middle figure you can see, and in the third figure you can see that the sampling frequency is taken as the actual frequency, which is half of the Nyquist rate, is undersampling. Okay, now similar another example they have taken with respect to hand of a clock, wherein it has only single hand. The clock has a single hand. With respect to that, how a sample can mean that the clock is moving either forward or backward. So they've just given an example with respect to Nyquist rate, again half of the period, a quarter of the period, and 3/4 of the period or the duration. And this was the first step in the uh, pulse code modulation, but the second step, or that is the quantization, is actually the result of sampling. It is a series of pulses with uh, amplitude values that between the maximum and the minimum amplitudes of the signal. So in this, we assume that the original analog signal has instantaneous amplitude between V min minimum and V maximum. So whatever values, we assume that the original analog signal has the instantaneous amplitude between the minimum values and the maximum values. So in order to get that uh, delta change in that, we need to divide the range into some zones. Let's imagine L zones. L, where L is the number of levels. So each height, or that delta, is will be equal to the maximum minus minimum values divided by that L value, right? So we, when we assign quantized value from 0 to L minus 1 to the midpoint of each zone, now we approximately the value of this sample amplitude to the quantized value. How? Because we are kind of finding an average or a midpoint of each zone, right? So in the quantized level, just when you see the slide, when you compare these slides here, uh, the midpoint of each zone is assigned a value from 0 to L minus 1, like I discussed, and resulting into L values. Now each sample falling in a zone is then approximated to the value of midpoint. So when we assume that a voltage signal with let's say V minimum as -20 and voltage maximum as +20, so we want to use L, that is number of levels, to 8 quantization levels. So the maximum height, or the delta you can say, the zone width is also known as zone width, is nothing but average of this with respect to levels. So 20, that is maximum voltage, minus minimum voltage, that is -20. So 20 minus -20 divided by L, which is 8 here, so that gives you 5L, value 5. So the total delta value here is 5. So when you divide these ranges, we can say, into 8 zones, we have -20 to -15 as one zone, -15 to -10 second zone, -10 to -5, then -5 to 0, 0 to 5, 5 to 10, 10 to 15, and finally 15 to 20. So the midpoint here, if you calculate, it will be -17.5, -12.5, -7.5, -2.5, 2.5, 7.5, 12.5, and finally plus 17.5 respectively. So when you assign the codes for it, that is the third stage in PCM encoder, that encoding, when the last step, sorry, the last step in the PCM encoding, that after each sample is quantized and the number of bits per sample is decided, each sample can be changed to a number of bit code words. For example, like each code is then assigned a binary code to it. Just when you see here, the number of bits required to encode the zones, or the number of bits per sample as it commonly referred to, is obtained by calculating the number of bits with respect to the log to the base 2 and the number of levels that you are taking. So in this case we have number of levels as 8. So because when you see the quantization levels in this example, in our example, we can see that the quantization levels we have 8. So log to the base 2 of 8, which gives you 3. So the number of bits we require to encode is 3. So when you name them, when you code them, these 8 zones or 8 levels you can say, we can name them like 000 as first level, 001 as second level, so on till 111 as our 8th level. Okay, so just when you see the or in other words, when you want to name it as in a zone, so when we have zone of -20 to -15, you can name that zone as or encode that zone as 000, and -15 to -10 as 001, and so on and so forth. And finally the zone which will be having, that is +15 to +20, will be encoded as 111. So this is the, in figure 4.26, it's given about the how quantization and encoding of a sampled signal can be represented. So all in all, when you just visually see the graph, you can see a rough plotting of an analog signal is done. A quantized format of an analog signal has been uh, presented here, with encoded, each zone encoded in a binary coded format. Now but there's one problem with this. Since we are approximating the values, there are chances of um, not reaching to the accurate values, or we can say not not landing on an accurate values, which can lead to what actually the signal is. So that will lead to an error. For example, if we take an approximate value of let's say the third sample, that is 16.2, if that is not the actual value, then there might be some errors because we are generalizing it. So in that approach there will be few errors. When we quantize, there will be few errors to it. So when a signal is quantized, we introduced an error, the coded signal, in an approximations of the actual amplitude value. So the difference between that, the actual value and the coded value, coded is nothing but the midpoint value that we have calculated. So the difference between these two values will refer to as the quantization error. Now the more zones, the smaller the delta. For example, when you see the graph here, when you have more zones or more samples, the more number of samples will lead to more number of zones, and the more number of zones will lead to a smaller delta value, that is the small uh, change, which will result into smaller errors. So the more number of samples we take, the better result that we get, in other words. But again, the more number of samples will lead to more number of zones and the more bits required to encode the samples. So in this example we discussed, we required only 3 bits to encode all the samples. But if we take more number of samples, more number of bits are required to represent that or encode those zones. So it will ultimately result into higher bit rate. So when we compare this quantization error with the earlier discussed concept of signal to noise ratio, so we can see that the signals with lower amplitude values will suffer more from quantized error, as the error ranges becomes half, that is which will be fixed for all the signal levels. So the non-linear quantization is used to alleviate this problem. Now the goal is to keep uh, signal to uh, signal to noise ratio fixed for all sample values so that there is uniformity. In order to do that, we can that can be done using two approaches, that is the quantization levels follow a logarithmic curve, that is nothing but smaller deltas at lower amplitude and larger deltas at higher amplitude. And the other approach is nothing but compounding. Compounding is the process in which the sample values are compressed at the sender into logarithmic zones and then expanded at the receivers. The zones are fixed in the height, so which will result into keeping our signal to noise ratio fixed. Okay, so having said that, there are few numericals which are discussed with respect to uh, bit rate. So when you consider example 4.14, uh, that is we want to digitize the human voice, what is the bit rate, assuming 8 bits per sample. So when you have the human voice normally, this is the assumptions or the general observation that they have considered, that the human voice normally contains frequency from 0 to 4000 hertz, so minimum 0 to maximum 4000 hertz. So the sampling rate and the bit rate can be calculated like, sampling rate is nothing but the maximum, what is the normal human frequency is half of it, sorry, the double of it is the sampling rate, and bit rate will be the samples per second and the product of the number of bits per sample. So since we have 8000 samples here and each sample has a bit rate of 8 bits, so that multiplies to 64,000 bps, which stands for 64,000 bits per second. So when you convert, it gives you 64 kbps. So talking more about encoding, the PCM decoder at the receiver side will contain few components like to a few components like PCM decoder, of course, and the input will of course the digital data, and finally the conversion that takes place from a digital data via PCM decoder, resulting into an analog signal. In order to do that, to recover an analog signal from a digitized signal, we have to reverse the process. That is, we use a hold circuit that holds the amplitude value of a pulse till the next pulse arrives. So we pass this signal through a low pass filter with a cutoff frequency that is equal to the highest frequency in the pre-sampled signal. Now the higher the value of L, that is more the number of levels, the less distorted a signal is recovered. So just when you see the diagram here, we can see that the digital data is the input for the PCM decoder, wherein a digitized format is given as an input to the decoder, which makes and connects samples, making it pass through the low pass filters and ultimately resulting into an analog signal, so that the receiver can again listen or understand those signals. Now just one more observation that they have noticed here, that when we have a low pass analog signal of let's say 4 kilohertz, and if we send the analog signal, we need a channel with a minimum of bandwidth of 4 kilohertz. So when if you can recall from the previous classes that we have discussed about the bandwidth depending on the channel, you can relate it here, that if we digitize the digital signal and send 8 bits per sample, we need a channel with minimum bandwidth of 8 into 4, that is 32 kilohertz. So that is the change here. Remaining concepts like how this what are the different modes of this transmission, or how different ways, in how many different ways we can transmit these signals, we shall discuss in the next class. Till then, if you have any queries, anything, any doubt, any clarification with respect to whatever discussed in today's lecture, you can post it in the group, provided it is related to the topic. Otherwise, you can ask me, text me personally. I can address those problems in the uh, as a general for complete class in the group. Avoid yourself from getting involved in any kind of chattings. If you have any queries, just raise it in the group, and that query will be addressed uh, in the group itself, so that if anybody else has same query, same questions, same doubts, will get the clarifications. Okay, so thank you and stay tuned for the next class.